Hello everyone, my name is Jidapa Plaimart. I'm originally from Thailand, but now studying a second year PhD at Newcastle University with Professor David Berner. So today I'm going to present about my work on biofiltration for microbial water quality management. So a bit of introduction. Biofilters have been successfully used for wastewater treatment over several decades. Wastewater treatment methods such as treating filters, low sand filter, and constructed wetlands use the ideal biofilter to treat wastewater. Sand and rock have been used as a filter media in a biofilter in several configuration types, and its performance can be intensified through the use of activated carbon within the filter media. So, what is activated carbon? The activated carbon is produced from a carbonaceous source material, such as coconut shell, sawwood, and coal. It has been widely used in wastewater treatment plants to absorb natural organic compounds, taste, and odor, particularly in the tertiary treatment step, as it is a highly porous material and provides a large surface area to which contaminants may absorb. However, the impact of AC amendment in biofilters on chemical pollutant and pathogen mitigation in wastewater needs more investigation. So this project aims to investigate the effect of coconut shell activated carbon amendment in biofilters on wastewater pollutants and human pathogen removal. I got two main objectives. The first one was to determine chemical parameters including DO, pH, BOD, COD, ammonia, nitrite, nitrate, phosphate, and heavy metals in the influence and effluent of biofilters with and without CFAC amendment. The second one was to investigate the abundances of bacterial pathogens in the influence and effluent of biofilter with and without CFAC amendment. So, in terms of hypotheses, it was hypothesized that the AC amendment of biofilters improved removal of BOD, COD, ammonia, as well as human pathogens compared to the biofilter without amendments. The second one is that there are more environmental bacteria in the effluent of CFAC amended biofilter than fecal in the case of bacteria. So I did a 1-month column study last September at KUTT in the School of Energy, Environment and Material. There were 4 columns. 2 columns with CFAC amended filter medium and another 2 controls without any AC amendment. The activated sludge effluent was used as a column influence, and it was collected from 2 crude wastewater treatment plants in Bangkok. The coal sand, gravel, and activated carbon were provided by the KUTT. And this is the column design. The wastewater was fed at the top and collected at the bottom. The columns were operated continuously for 2.5 weeks and fed daily by 785 ml of wastewater with 24 hours retention time. The column effluent was collected in 6 different days during the operational period. For the analysis, I did chemical analysis and microbial analysis. The conventional water quality parameters were analyzed in the column effluent following standard methods and heavy methods using ICP-OES. The column effluent and filter media were then analyzed for fecal bacteria and putative bacterial pathogens using a combination of mean-ion nanopore sequencing and quantitative polymerase chain reaction or qPCR. So, what are the qPCR and sequencing used for? The sequencing is used for the screening up to like 8 million bacteria in your sample and establishing their identity. Whereas the qPCR is used to quantify copy numbers of stickiness RNA genes and also quantify specific bacteria using like marker genes. For example, In your DNA sample, after sequencing, you will know that there are 2 of E. coli in 100,000 of all sequenced bacteria. Summarizing as relative abundance, which is the bacteria risk divided by the total success rate. And then after you do the qPCR will inform you that there are 2,000 gene copies of E. coli, which is the estimated absolute abundance. So meaning that you will know the estimated absolute abundance of bacteria by multiplying the relative abundance from the sequencing to the total stickiness gene copies obtained from the qPCR. Moving on to the results, many people here have discussed about chemical data, so I'd like to just briefly summarize my chemical data here in one table, and we'll focus more on the microbial data. So among the parameter measures, it was found that pH was higher in the effluent of the AC amended column. BOD and COD were removed by both control and AC column, and generally lower in the AC in every sampling event. Ammonia and zinc were also removed by both columns, but more in the AC amended column than the control. Moving on to the microbial data. I did the fecal coliform plate count, and the fecal coliform removal was 95 to 99% in the control and AC amended column, but slightly higher in the AC column, as you can see in the chart. Then I wanted to confirm the plate count result with qPCR. A specific gene qPCR for fecal coliform was used, and it was found that the result from the qPCR confirmed the same removal trends as from the plate count. Now, look into the DNA sequencing. The DNA from column, influent, and effluent were sequenced. I then selected 6 putative human pathogens listed in the UK Health and Safety Executive List. First 3 microbes can cause diarrheal illness like food poisoning. Last 3 microbes can cause infections. As evident in the figures, from day 2 results, it was found that the selected pathogens were generally removed in the both biofilter with and without AC, with a better removal from the AC column. On day 4, the abundances were decreased by 100 times, and mostly still lower in the effluent of the AC column. Now coming to day 10, it was still showing the same removal trends as in the previous sampling. So in conclusion, CSAC was therefore able to reduce the abundances of the selected pathogens. The DNA in the filter medium was also sequenced for stickiness RNA. It was found that there were higher stickiness RNA gene copies in the filter medium AC column both before and after filtration than that in the control, meaning that bacteria could possibly be hiding in the pores of acrylic carbon. So then I looked deeper into human pathogens in the filter medium, and it can be noticed that the filter medium in AC column show 1,000 times higher abundance of Pseudomonas aeruginosa than in the control, providing another evidence that human pathogens were perhaps also retained in the AC pores and protected from predation. A bit of microbial ecology. It was found that fecal indicator bacteria were reduced in both biofilters relative to the abundance of other bacteria, meaning that there was a shift of a human gut influenced microbial community to environmental related community after biofiltration. The fecal indicator bacteria, or maybe known as the gut bacteria, are kind of competitive in the human gut, but they're less competitive than environmental bacteria in the filter environment. And that's the reason why the environmental bacteria then predominated in the column effluent. The AC column effluent also showed lower relative abundance of gut bacteria, or on the other hand, higher abundance of environmental bacteria than the control in day 4 and 10. And these are the conclusions. Firstly, BOD, COD, ammonia, and zinc were removed more in AC amended column than the control. Fecal coliform removal was about 97.5 to 99% in the AC amended column, which was slightly better than the performance of the control. Several species of putative human pathogens were also found to be reduced by AC biofiltration. More bacteria, including putative pathogens, were retained within the AC method as compared to the control column, perhaps because of the bacterial mutation in the STS-AC pores. And finally, the fecal indicator bacteria were reduced by both biofilters, meaning that there was a shift of human gut influences by the microbial community to environmental related community following biofiltration. And I'd like to thank these people, both from Newcastle University and UTT, for their assistance and support throughout this study here. It was a great month here to study in Bangkok. And that's it for me today, so thank you very much for your attention.
Thank you so much, Ms. Plaimart. It was such a wonderful presentation. I didn't see any SEM or TM analysis in your work. Did you do any SEM, scanning electronic micrograph, or TEM analysis? Because you talk about the pore size of activated carbon, and then you said in your conclusion that perhaps there are pathogens or bacteria that may have moved in the pores. If you talk about the pores, did you analyze your samples? If it was mesoporous or microporous or macroporous? And then if you analyze that one, and perhaps if you do TEM or SEM, and then you can compare the bacteria size and also the pore size, and that's how we can find out the mechanism and where it goes. Thanks.
I actually haven't this SEM or TEM for this coconut chocolate carbon that's provided by the community here, but I did some screening at Newcastle for the aggregate carbon, but it also was produced by coconut shell. I don't know, maybe from different company of different source. And I just did calculate for the total porosity and micropore, and I found kind of high, it has higher porosity, high porosity. It had high porosity and surface area, and that's why I think that the microbe might be able to kind of escape to that pore in the filter column, and then kind of preventing them from to being eaten by other protozoal kind of other organisms. Yeah, I'll do that later on. Yeah, sorry, thank you for this.
So, yeah, we waited you to visit India, but you didn't come. My question is that is it intentional to take the sample on first day, second day, 10th day? And what was the logic behind how long you will run the column test? And by what science behind that is the interval with which you have collected the sample?
The experiment was conducted for 2.5 weeks, and then I kind of collected the effluent like every other day. So I just show the day 2, day 4, and day 10 results here. Yeah, to see the trend.
We still have some minutes for other questions.
Okay, one more. Why you have selected specifically 785 ml or something?
Yeah, 785 now to the column, right?
Yeah.
Because due to the based on the hydraulic loading rate of, like you can see like 10 centimeter diameter of the water column.
Oh, so that contains 785.
Yeah, that's the tropical hydraulic loading rate in the tropical countries.
Okay.
One last question. Just this one. What is the size of the sand and activated carbon you have used for this filter media? The size, the particle size, yeah.
Well,
Is it a mixture? Is it a mixture or like the same size? For sand?
For the sand.
Yeah.
I think normally the whole thing is a for sand. I haven't measured diameter.
Because my concern is like if you mix up like bigger and smaller, the smaller size will fit in the bases and maybe it will block the way, so the water may not be able to. So that's my concern, like what sizes you have used?
Yeah, so I selected kind of bigger grain size of sand in the column. So to avoid, I thought like if you use like a kind of tiny sand, and it can kind of the clocking can be more bigger. So I selected the bigger grain size, and I didn't get any clocking problem.
So if there is no more question, thank you, Jidapa. So we will move to the next presentation.